All right, guys. Let's get situated here. Yeah, sorry, my room was used yesterday for testing, so maybe some of the desks are not calibrated. I don't know what decade I'm in, I'm kidding. We got 70s, we got 80s, we got 90s. Y'all are funny. Rihanna swung by yesterday, and she's like, you know what? I'm going to make these notes. So Rihanna typed all of these notes out. Thank you, Rihanna. I'm reusing my jokes from last year, So here it is, guys. Related rates. I should have put it on the canvas. I'll try to be better about it. A lot of this is pretty much just straight physics, and this is stuff that you would watch or see in a calculus-based physics class. We don't have calculus-based physics at this school. We just have regular physics. But maybe in the next 3-4 years, we will start offering calculus-based physics. And here is how calculus-based physics would look like. Cool? All right, so check it out. So it says, you always got to make a relationship between something, right? It says, assume that the radius r of a sphere is differentiable function of t. So that means that this sphere is either getting bigger or smaller. One of the two. It's either getting bigger or smaller. And let v be the volume of the sphere. Find an equation that relates dv dt and dr dt. Okay, does everyone know what's going on? So, all right, let's start with basic English. Whenever it says it's differentiable with respect to t, that means that this sphere is moving. It's not moving as in the whole sphere is moving right or left. Moving as the sphere is getting fatter or thinner. So with respect to time, with time, something's happening to the radius. It's getting larger and larger. You know what I mean, guys? Does that make sense? The dr dt means the radius is moving. All right. So before we can even answer this question, is there a relationship between volume and radius for a sphere? Yes. Yeah. What's the equation? You got to remember it?
No.
I think it's 4/3 pi r cubed.
Yeah. They give you the formula.
I don't know why I don't like it though. Do you guys agree that that's what it is? I don't like it, but all right, let's Google it really quick. Oh, you know what? Let me try this. Hey Siri, what's the volume of a sphere?
A sphere is a geometrical object in three-dimensional space.
No, I want the volume. See, technology is not there yet, guys. Four-thirds pi r cubed. We're right. All right, here we go. You guys ready? Yes. So there's my equation. I'm going to take the derivative with respect to time. So dv dt, don't write v prime, write dv dt equals 4 pi r squared, but we took the derivative not with respect to r, but with respect to t. And there it is. Done. That's it. That's the relationship.
Wait, hold on.
The 4/3 pi r is a constant.
Oh.
So it's like, what's the derivative of x cubed? 2x squared? Or 3x squared? So I brought the 3 down. So 4/3 times 3 cancels out. So 4 pi r squared dr dt. Right, guys? Okay. Yeah. And there it is. That's it. That's all they wanted. Cool? Or not cool? I took the derivative with respect to time. So I wrote dv dt because I'm taking the derivative with respect to time. What? In the end, it's dr dt. Because I took the derivative of r with respect to time. R is the variable that I'm differentiating. But I'm differentiating it with respect to time. So dr dt. You know what I mean? Okay. All right, so the next letter says, assume that the radius r and height of a cone are differential functions of t, and let v be the volume of a cone. Okay, volume of a cone, this one I know, is 1/3 pi r squared h. So I'm going to write pi over 3 r squared h. If you go to Google, it might put the 3 somewhere else, but it doesn't matter. It's still the same thing. You guys ready? So when I take the derivative of this one, I got to do what rule? I don't know, Travis. Yeah, well, power, but more specifically, I have how many variables here? 2. It's a product, so I got to do product rule. So here we go. dv dt equals, and this is a constant, so do you want me to leave the constant alone, or do you want me to pair it with the r squared? It doesn't really matter. Pair it with the r squared. Okay, it doesn't matter, guys. Whatever you're most comfortable with. I'm going to pair the pi over 3 with the r squared. So that's first and that's second. Do you guys see that? If you don't want to do that, leave the pi over 3 on the outside. It's the same thing. So here we go. First, pi over 3 r squared times the derivative of the second, dh dt, plus second, h, times the derivative of the first, 2 pi over 3 r dr dt. Do you see what we did? Okay, so here's my final equation. Let me make it look pretty. dv dt equals pi over 3 r squared dh dt plus 2 pi over 3 rh dr dt. And there it is, guys. I think it would have looked prettier with the pi over 3 factored out, but that's fine. What's up, miss?
Did you explain why you put the DRT2 again, like next to the 2 pi over 3 r?
Why did I put it right here? Because I took the derivative of r with respect to time. So the derivative of r squared is 2r dr dt. But then I multiplied the 2 times the pi over 3, right? Maybe it would have been simpler. Don't worry, I see you, miss. Maybe it would have been simpler if we would have done it like this. V equals pi over 3 r squared h. And you see how I put the bracket there on the r squared h? Maybe it would have been simpler if I would have left the dv dt equals, leave the pi over 3 on the outside. First, r squared times derivative of the second, dh dt, plus second, h, times derivative of the first, 2r dr dt. Maybe that would have been simpler. And then distribute that. What's up?
So, is it like how we do like UR dx, but then y is not x, so that's what we do like y.
Perfect. So Parker said when we did implicit derivatives, when we took the derivative of y, it was dy dx, right? Y squared, the derivative of y squared is 2y dy dx. But when we did the derivative of x, it didn't have anything, because that's because it's dx dx. Same thing with this. It's not. I'm taking the derivative of r, but with respect to t, so it's dr dt, right?
And then when you take the derivative of h,
Yes, eventually. Like the derivative of h squared is 2h dh dt. If it's by itself, the derivative of h is dh dt. But if it's h squared or h cubed, then chain rule, right? 3h squared dh dt.
okay.
Well, all right so far, guys? I know we haven't done calculus in a week, like real, like new stuff. All right, so that's it. And now after that, we're supposed to know everything and do this. So let's see if we can. Don't worry, we're gonna go slow. Example 2. A spherical snowball is melting in such a manner that its radius is changing at a constant rate, decreasing from 21 centimeters to 10 centimeters in 30 minutes. At what rate is the volume of the snowball changing at the instant when the radius is 3 centimeters? Okay, what do they want? At what rate is the volume of the snowball changing? What does that mean? What is that? So it's melting, it's shrinking. So what do they want to know? Like what unit do they want to know? Volume, dVdt, drdt, dVdt. They want to know dVdt, guys. So before we can do anything, do we understand that they're asking for dVdt? Yes. It says at what rate, so underline, at what rate is the volume? At what rate is the volume of the snowball changing? So if I want to know the rate of the volume, isn't the rate of the volume dVdt?
So it's like
Is the instantaneous rate of change of the volume? Yeah. Cool or not cool, guys? Okay, so what did we say volume of a sphere was?
4/3
Pi r cubed. You're right. 4/3 pi r cubed. All right, here we go. I'm going to find my dVdt. So I'm going to write dVdt equals, the 3's cancel out, 4 pi r squared dr dt. All I need is radius and my dr dt. Do they give me a radius? Do they give me dr dt? They do. It's embedded in the question. It's decreasing from 21 to 10 in a matter of how many minutes? So my dr dt is equal to 21 minus 10 over 30. It's decreasing from 21 centimeters to 10 centimeters. I feel like I should use a negative because it's decreasing. The word decreasing means it's getting smaller.
Yeah, but final minus.
Yeah, so then final 10 minus 21. Okay, 10 minus 21. There. Takes care of it. Are we okay so far, guys? 10 minus 21, what's that? Negative 11? Negative 11 over 30. And I need units, centimeters per minute. I got everything I need. So let's see. My dV, that's dr dt, by the way. My dV dt is equal to 4 times pi times 3 squared times negative 11 over 30. And all this, if you multiply all the units, I think it's going to be cubic centimeters per minute, which is fine. That's the units we want. Let's see. 3 squared is 9. 9 times 4 is 36. 36 times 11, I don't know. 36. I have a calculator here. Or let's just use the calculator that we have here, right? Let's get our calculator out. Yeah, get your calculators out, guys, because you're gonna need them. Three squared. 4 times 3 squared. I'm not going to multiply the pi because I'm going to leave it in terms of pi times 11 over 30. (66 pi over 5) negative. Cubic centimeters per minute. Because centimeters squared times centimeters is centimeters cubed. And then over minute because the time was in minutes. How do we feel, guys? And that's it. That's all it is. Don't worry. We're going to do a whole bunch of problems. Because Rihanna wrote a whole bunch of problems for us. Yeah, she's a diva. That girl Rihanna. Nah, diva, miss. You know what? Taylor Swift will write the next one. I got the connections. All right. Oh, maybe. I don't know. Maybe I'll do Rihanna today during lunch. All right, here we go. Example 3. A highway chase. No, miss. A police cruiser. All right, guys, focus. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? Whoa, did we take all that in? Yeah, read it again, guys. Read it again to yourselves. right-angled intersection. Okay. The key to tackling this question, guys, is to draw a picture. So draw a picture. Did you draw a picture? Okay. So there it is. I drew it according to their plans. Okay, so one warning when you're drawing pictures, do not, under any circumstance, put 0.6 here and 0.8 there, because if you do that, you're making this static. It is no longer moving. If you do that, you're telling me that that distance is always 0.6 and that distance is always 0.8. Is it true that that distance is always 0.6? No, because it's moving. So whenever something is moving, it's best to use letters. Because this is going up and down, it's vertical, what letter do you think I'm going to use? Y. You can use it, yeah, you can use Z if you want. You can use any letter really. But because it's vertical, we've been accustomed to using the letter Y. Because it is horizontal, what letter do you think I'm going to use? X. See? And then for the hypotenuse is growing also. If you want to use a letter, Z, or A or whatever letter you want. Cool or not cool? What's up? As long as you're consistent, I guess it won't for the answer. But I drew it the way this. It told me the cruiser was north, so I drew it north. It told me the bad guy was moving east, so I drew it moving east. See? Cool, right? All right, so there it is. When the cruiser is 0.6 miles north of the intersection, so here's the intersection. So that means Y is 0.6. So put that on the side. Because we're looking at a moment. And the car is 0.8 miles to the east, so X is 0.8. Does everyone know where those values came from?
Yes.
Okay, perfect. And then they tell me how fast this police car is going. How fast is he going? 60 miles per hour. But we got to take velocity into account or direction into account. The way I drew this, if he's going 60 miles per hour, is he going north or is he going south? So I'm going to write the y dt, and I'm not going to put positive 60. I'm going to put negative 60. Miss, I thought you were a teacher.
Everyone can tell me that.
Yeah, no, it's like, is this Miss Brown? I thought it was Miss Brown initially. I thought Miss Delmer was the student initially.
Did you see the shoes?
Yeah, she's all rocking now.
No, a student ran into her and she was like, ah, and I was like, she's gonna step on it.
All right, let's focus, guys. They want to know, what's the question that these guys want to know? They want to know the speed of the bad guy. So they want to know dx dt, question mark. We're going to use calculus to figure this out. You guys ready? Now, they give me a piece of information. I want to know what this is. The police determined with radar that the distance between them and the car is increasing at 20 miles per hour. What is that 20 miles per hour?
Acceleration.
No, it's not acceleration. Is it dx dt, dy dt, dz dt? I don't know. Where's the radar in a cop car located? In the car, right? So it's a line of sight between the cop car and the bad guy. So it's dz dt. dz dt is increasing at a rate of 20 miles per hour. Does that make sense? At that moment, he is getting further and further away. Because the way I drew my picture, down is negative and up is positive. He's going, it's a bird's eye view. I'm just talking about two directional motion, X and Y. So this cop car, he's going in this direction, down. Yeah, well, he's moving down. Yeah. And then the bad guy is moving to the right. If the bad guy was moving to the left, he would have been a negative. But the bad guy's moving to the right. Well, I mean, who knows? Maybe he didn't do anything bad. And the cop is just chasing them just for fun or something. Okay. All right, are we okay so far, guys? Any questions about the directions or anything? Okay, so here we go. I need something, a relationship that will connect X with Y with Z. Is there anything you can think of that puts all three of them together? Oh man, I took a course called geometry. Did we learn something in that class? Pythagorean Theorem. Pythagorean Theorem gets all three variables, X, Y, and Z, and connects them. So that's the key. Is there a connection that can put all three of them together? Yes. So here's what you're going to write. You're going to write X squared plus Y squared equals Z squared. You guys all see that triangle, right? Okay, and then you ask yourself this question. Is this moving with respect to time? Are the lengths moving with respect to time?
Yes.
They are. So that means this is differentiable with respect to t. So that means I can take a derivative with respect to t. Does that make sense? So here we go. Here's where the magic happens, guys. What is the derivative of x squared? 2x, but I'm not taking it with respect to x. I'm taking it with respect to what? T. So what do I write right next to it? Perfect. Plus, what's the derivative of y squared? 2y dy dt. Equals, what's the derivative of z squared? 2z dz dt. And then the math that you're doing right now is the same math that NASA uses when they're finding projectile motion, meteor going around something. It's the same thing, but more complex, 3-dimensional, not 2-dimensional. And then sometimes 4-dimensional because they'll have a fourth variable, time. All right, are you guys ready? So we got everything we need. If you wanted, you can cancel out the 2's. If you feel like you can, which you can. You can factor out a 2 there. You can factor out a 2 there. So you can cancel them all out. Divide everything by 2. Does that make sense? All right. Look, guys, you have everything you need. I like to actually plug it in now. You have x. You don't know dx dt. That's what we're looking for. You have y. You have dy dt. You have z, but not directly. And you have dz dt. Yeah, you have z, but not directly. Look, you have x and y. And didn't you just tell me that this is a relationship? So I can get z by just doing Pythagorean Theorem, right? So on the side, I'm going to go z equals the square root of 0.6 squared plus 0.8 squared. So z is the square root of 0.36 plus 0.64. Z equals 64 and 36. I think that's 1. Yeah, z equals 1. Well, they give you pretty numbers. Okay, now we got everything we need, guys. Here we go. If you want to isolate dx dt, which is probably what you do in physics, if you want to isolate dx dt, put it by itself, you can. I like to just go ahead and plug the numbers in and then get dx dt by itself. So here we go. X is 0.8, so I'm going to write 0.8 dx dt plus y is 0.6. 0.6 dy dt is negative 60 equals z, which is 1, times dz dt, which is 20. So now you're done with the calculus part. Now it's just algebra. So let's see. 0.8 dx dt minus 6 times 6 is 36. So 60 times 0.6, I want to say, is also 36, equals 20. Are we still okay? I'm going to add 36 to 20. So 0.8 dx dt equals 36, 46, 56, equals 56. Are we still okay? And then how do I get dx dt by itself? Just divide by 0.8. Oh, now I'm going to need my calculator. Dx dt is, let's see how fast, what is it? 70? Oh, it's going pretty fast. I was expecting them to go faster, but that's fine.
And so the whole, like you said, the key to figuring this out was the connection, which we had to come up with, like, the 13 hour and the 5 hour. And then for the other ones, it was like the volume.
It was, yeah. So the key is find a connection of how they're related. There is always some type of connection. Either there's a common shape, a rectangle, a triangle, or something. You know what I mean, guys? So let's see what we got next. Ooh, I like this one a lot. No, you're going to like it. It's a rising balloon. So, a hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from liftoff point. Okay, so sketch a drawing. Not yet. Well, you can if you want to start. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Oh, wow, I like this question. What if you worked for NASA and they give you this question right here? Could you do it? No, you say yes. Yes, you can. Yes, you can. I like this question. So let's first draw a picture. So let's draw a picture, guys. So let's see. Draw a flat surface. Here's your rocket. How do I draw a rocket? Hot air balloon. Sorry. Here's my hot air balloon. I'm going to draw the hot air balloon already somewhere up here. Hot air balloon. There it is. I'm measuring right from the center. Here is the Pathfinder, the little thing that measures. And it said this was static. That horizontal distance is how much? So that is okay to write 500. Because that is not changing. Does that make sense? Okay, if something is changing, don't write numbers if it's changing. This height is changing. What letter do you want to use for height? We can use H, I guess.
Yeah.
Okay, H. Instead of the typical Y. That's fine. And then the track finder. And this is obviously a right angle right here. And let's see. Let me see what else I can put in there. The angle is right here, guys. Do not put pi over 4 because that's making it stuck. Put theta. A hot balloon is rising straight up from a level field is tracked by a rangefinder 500 from liftoff. At the moment, the rangefinder elevation angle is pi over 4. The angle is increasing. Okay. The angle is increasing at a rate of 0.14 radians per minute. So on the side, write d theta dt equals 0.14. Remember that one full revolution is 2 pi. Okay, which is not going to do, obviously, but so that way you have a picture of what's happening. Okay,
That would technically would that be like our correspondence?
no, that's just the d theta dt equals 0.14 is just telling you how fast this angle here is growing.
Oh, okay.
You know what I mean? What's up?
So what is the elevation next to the power?
That's a theta is pi over 4. You're taking a picture when theta is pi over 4.
And then that's just the rate that it's increasing.
Yes. If you're wondering, pi over 4 is 45 degrees. Does everyone agree with that? So technically, they're taking a picture when this angle is 45 degrees. But we don't work with degrees. We work with radians all the time. Are we okay so far, guys? Okay, because if we work with degrees, it would make this a mess. Because we have an extra factor of pi over 180. You don't want to deal with that. Trust me, it would look nasty. Okay, here we go. I need a relationship between H and theta at 500. Let me give you guys a hint. Yeah. SOHCAHTOA. You guys remember that? So with respect to the theta, which one uses 500 and which one uses H? Tan. So that's the one that I'm going to lean on. If you want to calculate the hypotenuse, you can, but why do you want to deal with two things that are moving? Because remember, the hypotenuse is changing. Why do you want to deal with two things that are moving when you can just deal with one? Does that make sense? So you would get the same answer if you use sine or cosine, but it would take you longer because you have more moving objects. Cool? So here we go. I'm going to write tan of this angle, theta, is equal to opposite h over 500. And that is safe because the 500 is static. It's not changing. Are we okay so far? All right. From there, I think this is simple enough that I would get h by itself. So I'm going to just multiply both sides by 500, and I'm going to write it like this. I'm going to put an arrow, and I'm going to write h equals 500 tan theta. And now we're ready. You guys ready? What question did they even ask? How fast is the balloon rising at that moment? What do they want? Not the hypotenuse. The dh dt. That's what they want. So let's use our advent strategies. Sorry guys, I just wanted to throw shade. I'm not okay. I didn't mean that. I'm not throwing shade at anyone. Okay. So here we go. I really am sorry. I hope I didn't offend anyone, guys. It's because I was told to use wicker skills from that lady. Here we go. Ready? Taking the derivative with respect to what? T. dh dt is equal to that 500. Leave it alone. What's the derivative of tan? Perfect. Am I done? No. I take what did I put right next to it? D. No, you're right. D theta over. Perfect. It's like chain rule, derivative of the inside, d theta dt, right? All right. Do I have d theta dt? Do I have theta? So here comes your pre-cal, not extreme pre-cal, just baby pre-cal. 500 secant squared of pi over 4. And then the theta dt was 0.14, 0.14. So here we go. 500, open parenthesis. Secant's the reciprocal of cosine. Well, I guess it doesn't matter at pi over 4 because they're both the same. So the reciprocal of square root of 2 over 2 is 2. There was a mosquito in the air. 2 over square root of 2. Square it and multiply it by 0.14. So let's see what we get. 500, 2 squared is 4. Square root of 2 squared is 2. 4 divided by 2 is 2. So 500 times 2 times 0.14. So 1,000 times 0.14, what's that, 140? 140 feet per second. That sounds pretty fast for a hot air balloon. In 1 second, 140 feet. Oh, okay. Minute's way better. Yeah, there. Okay, that makes a lot more sense. 140 feet per second is way fast for a hot air balloon. But,
Have you ever been in one?
no, but I've seen them on TV. But for 140 feet in 1 minute, yeah, 2 feet a minute, 2 feet a second sounds reasonable. Yeah, 2 feet a second. Yeah, it's slow. So there it is. Always make sure that your numbers make sense, guys. Are we cool or are we not cool? All right, now we gotta. Can we take some more or no, guys? All right. This is our second to the last one. You okay, Moreno? If you want to take a break, go for it. All right, example 5, guys. Water, oh, you got the good stuff. Water runs into a conical tank at a rate of 9 cubic feet per minute. Before you even start, what is 9 cubic feet per minute? Yeah, what is it? Like, is it DRDT? What? It's DRDT? Cubic feet per minute? dVdt. dVdt is 9 cubic feet per minute. Well, I don't know. Let's read. Let's see what's up. The tank stands point down and it has a height of 10 feet. So I'm going to write height is 10 feet. Well, the height of the tank is 10 feet, so I'm not going to write that down. And a base radius of 5 feet. Now, those are constants, so those you can write. How fast is the water level rising when the water is 6 feet deep? Okay, let's draw a picture. This tank is Water, the tank stands point down. Okay, so here it is. It looks like this. Here's the base of the cone, and it's a cone. Well, it tells you the cone, right? Conical. Conical means cone, right? Oh man, guys. Conical means cone. I'm gonna talk to our geometry teacher and make sure. What does conical mean? Cone. Now don't go to your raspa stand and give me a conical shape. Like conical means cone, guys. All right. Whatever is static, it's okay to write numbers down. And there's two static numbers that they gave me. They gave me the base radius, which means this. That's a base radius. And that base radius is always what? 5. And they gave me the base height. The height of the cone is always 10. So that is true all the time. Now I have water in there. How fast is the water level rising when the water is 6 feet deep? So here's the water. I'm going to put it right here. So actually, it's going to look more like, but of course it's wavy there. But there's the water. And this is how deep the water is. And I'm going to call that H. Is that okay?
Why do we call it H?
We can call it whatever we want. We can call it W. Yeah. Are we okay? All right. Let's see. How fast is the water level rise? Okay. Well, the water that's in here is going to take the shape of what shape? A cone. What is volume of a cone? We just did it earlier. Pi over 3 r squared h. Put that down somewhere. So here's the deal. We're going to need dr dt. We already have dv dt, but we're going to need dr dt to figure out this answer. Does that make sense to you guys? So here is my r. So let me see if I can do it in green here. So here's the r that we're talking about. I wanted to go to the middle here, but it's not calibrated. Do you guys see that r right there? Yeah, let me zoom in. That r in green. As this water level increases, that r is getting larger and larger. Yes or no?
Yes.
All right. Focus, guys. Chirella, focus. I want to make sure you guys are good on this. So remember, the water is going up on this tank. So as the water goes up on this tank, that r is getting larger and larger. Yes? So we need to figure out a relationship first. Before we even start, we need to figure out a relationship between, we got to figure out how we're going to figure out what r is. Because they don't give us r. They just told us that h is 6 feet deep. That the water is 6 feet and rising. Does that make sense, guys? So let's figure that out. And we're going to do that with geometry. So remember what we call this distance. This distance is h here. So how are we going to find it with geometry? Like this.
Isn't it just like a similar?
Yeah, similar triangles. So I'm going to write 5 over 10 is equal to r over h. Remember, r and h are changing. Cool or not cool? All right, so if I separate these variables, let's see. I mean, you don't have to, but I'm going to. Cross multiply. So 5h equals 10r. Did I do that correct? And we wanted to get r, so I'm going to divide by 10, divide by 10. So can I write half of h is equal to r? Okay. So from there, we're going to do two things. First, we're going to find out the moment, at that moment when h is 6, what is r? So if h equals 6, because that's how deep this water is, r has to equal, what's half of 6? Not everyone at the same time. 3. So there's one relationship. The other relationship we're going to get, we're going to take the derivative of that with respect to what? Time, right? So dr dt is equal to 1/2 dh dt. Yes. I need that relationship. Because I'm going to need that relationship when I take the derivative of volume over here. Are we okay? Here we go, guys. You guys ready? I'm going to take the derivative of volume. With respect to what? T. So dv dt is equal to, and maybe for you guys at the moment it's easier to leave the pi over 3 on the outside. It does make it prettier, I think. First, r squared times root of the second, dh dt, plus second, h times root of the first, 2r dr dt. Do I have everything I need? I actually do now. dv dt, check mark. Radius, check mark. dh dt, that's what we're looking for, so x. Height, check mark. Radius, check mark. dr dt, yes, through this. So I'm just going to plug in my substitution, 1/2 dh dt for dr dt over here. So I can have everything in terms of dh dt. That's what we're looking for, right? dh dt. So here we go. My, should I do it now? No. Let me first replace it. dv dt equals pi over 3 r squared dh dt. And all I'm doing, guys, is replacing dr dt. So I'm going to write plus h 2r, and then I'm going to write it in parentheses what I'm replacing. So here we go. I'm replacing that with 1/2 dh dt. So here's a good color coding if you're using colored pencils.
So you found the DRDT, so that when we do this derivative for dv dt, have like all of your things are known so that you can get the dv.
This is going to test your algebra skills, guys. So here we go. Oh, okay. Now I'm just going to I'm going to make it prettier, and after I make it pretty, I'm going to replace what I know. So dv dt equals pi over 3 on the outside, parenthesis, r squared dh dt, plus that 2 and that half, they're going to cancel each other out. So I'm going to have hr, or maybe I should have written rh. It doesn't matter. I'm just trying to make it pretty. RH dh dt, close, I guess I don't need it, bracket. I'm ready now, guys. I'm going to plug in numbers.
Yeah, but would you not multiply the 2r by the dt?
I did. H times 2 times r times half times dh dt is rh dh dt.
Yeah, I know.
Yeah, I multiplied everything, miss. That 2 and that half made it 1, so now I have hr dh dt. I just put the h in the front. But all this is multiplied. Right? You okay or no? Okay. Here we go, guys. I'm just plugging in now. What was my dv dt? 9. Pi over 3, bracket. What was my r? No, that's not. I don't want that r, because that's not. That's the r way up there. I want the r of the water. 3. The r of the water is 3. So 3 squared. I'm gonna go ahead and write 9. 9 dh dt. That's what we're trying to figure out. Plus 3 times the height, which is, and then dh dt again. So there it is. So now we're done with calculus. Now it's just algebra. So let's see. 9 equals pi over 3. Let's see. That's still 9 dh dt. Plus 6 and 3. That's 18 dh dt. And then 9 equals pi over 3. 18 plus 9, is that 27? 27 dh dt. And then 3 goes into 27. 3 goes into 27 how many times? 9. So there's going to be 9 pi dh dt. And then the last step, how do I get dh dt by itself? Divide by 9 pi. So my dh dt is equal to 1 over pi, and I need units. Is this feet per minute? Feet per minute. There it is. Don't worry, we're going to do this a different way. I'm going to upload this online so you guys can see it again. Sorry, okay. You guys got enough sleep yesterday, right?
I was up till 3:37 in the morning.
Oh man, guys. All right, here we go. Maybe you thought that was torture. If you were to put this in the junior high, would they be scared?
Yes.
All right. Here's what I'm going to tell you guys. Make life simpler for yourselves. Is there another way to do example 5? There's always another way to do any problem. Just like a long time. Remember, Ms. Parker, we were doing a question and you were like, well, I saw it this way and you did it a different way, but we still got the same answer. There's always a different way to do a problem. So here it is. Let's just sketch this again real quick. So here's the water. That's R, that's H, that's 5, and then that's 10. All right, volume, pi over 3 R squared H. All right, here's the key. Ready? If you don't want to work with two variables, because remember, all of these things are changing. This is changing with respect to time. This is changing with respect to time. That's changing with respect to time. The question's asking how fast is the water rising. So what they want is dHdt for the water. Does that make sense? The radius is changing with respect to time, and we already got dVdt. That was 9 cubic feet per minute. Guys, you can replace the R. You can replace the R with geometry like we did a little while ago. So what did we say? We said 5 over 10 is equal to R over H. Do you guys remember that? And then we said, what did we say? We said 10R is equal to 5H. And then we said divide by 10, and we said R is equal to half of H. Or write it as H over 2. We said H over 2. Didn't we say that? Well, you could have gone right off the bat and said, oh, R equals H over 2. And you could have just plugged it in right there. And you got a volume formula in terms of H. This is the stuff that you should have been doing in geometry, like messing around with it, solving it, like giving you this type of questions. So now, if you rewrite this equation for volume in terms of H, volume equals pi over 3, open parenthesis. What is radius? H over 2, square it times H. So let's see, volume equals pi over 3. H times H is H squared over 2 times 2 is 4 times H. And now I'm going to simplify it. Pi over 3 times H cubed over 4. And now let's put it all together. Volume is equal to 3 times 4 is 12. Pi over 12 H cubed. So now you got a volume formula just in terms of the height. Cool or not cool? So now look how much simpler this is. We better get the same answer. If not, then I'm a fraud, right? So I'm going to take the derivative of this, and I'm going to get dHdt, and it better be the same. So let's see. What am I taking the derivative of this with? With respect to what? Time. So dVdt is equal to, move the 3 to the front, 3 pi over 12, and a little bit we'll reduce that, H squared dH dt. Do you guys agree that that is correct?
Yes.
All right. Let me reduce it. So dV dt is equal to pi over 4, because 3 goes into 12 4 times. And then it's H squared dH dt. Now I'm ready. Let's see. dV dt was 9. So 9 equals pi over 4. The height was 6. So 6 squared dH dt. Now I'm just going to solve for dH dt and see what's up. 9 equals 6 squared is 36. 36 divided by 4 is 9. So 9 pi dH dt. Divide by 9 pi. Divide by 9 pi. OMG, look at this. dH dt is equal to 1 over pi feet per, was it minute? Minute. Did we get the same answer? All right, so I think that's about as much as we can handle. I have an activity for you, but I don't know if you guys want to do the activity. Would you guys prefer to do a delta? Okay, so let me turn on the delta first then, and then I'll give you the activity tomorrow. All right, so take a 2-minute break.